Hello, in today's video we're going to talk about impedance matching for reasons because I've had trouble in the past dealing with it, what is it exactly, and implementing this into my own designs and whatnot. So I thought this might be a good video to make on for those who are having trouble with it, want to know a bit more about it. This is just going to be a basic overview and to what is it and what it's actually used for. So let's start with what is it. Necessary part in RF circuit design, impedance matching allows the maximum possible transfer of power between a source and its load. What this means is when you have that RF line from, this is primarily from microcontroller design I'm going to go over, you are sending it's a transfer power, as it says, from one end to your antenna. And because there is, you'll see this thing where there's a difference in load resistance from its source and its load. And let's say, for example, your microcontroller RF portion has a 50 source and your antenna has 75 ohms. So you need something in between this that allows both the source and the load to see each other as a 50 ohm, for example. So you want it to be 50 ohm on the source, 50 ohm on the load. And this circuit in between, this impedance matching circuit, helps to achieve that. So that in this prevents losses and reflections within your circuit because of this. So it's very useful, in fact, and it's quite necessary. How's it done? As I said before, that there are loads of filters and whatnot which you can do in between, and here are a few of them shown here. This was taken off a book by RF Circuit Design by Chris Boswick, I believe it was. So I highly recommend that to do a bit more further reading if you are interested in it, and it goes over about how you can calculate it and whatnot. But for this video, we are showing you how to get up and ready to do this type of thing. A more common one that you'll see is this pi filter right here, and as you could tell, it's called this because of the Greek letter pi, and quite usually a capacitor here, inductor here, and a capacitor over here. And there are quite few examples of this, but quite usually the manufacturer and your chip of choice would provide a way to impedance match it, as you see in the reference designs and whatnot, which we'll come take a look at. So let's take a look at this chip right here. It is an STM32WB55 ultra low power dual Encore Cortex M4, yada yada yada. And you can see it has Bluetooth low energy, and this would be our RF portion of it. So let's take a look into its data sheet to find out what exactly are we looking for when we come to a microcontroller of choice. Here in its datasheet, we have 196 pages of pure goodness, and we are looking for the RF portion. Now, I always tell you to read it carefully because there are so many times, I've missed certain designs and I have to go back and redo. Such simple mistakes could have been avoided. So when you go to your datasheet, you don't really need to read all 196 pages if you know what you're looking for, but quite usually ST is very kindly separated into all these different portions, and what we're looking for here is the RF portion. So we see 3.6 RF subsystem. Let's click on that, and I would recommend to read through a bit of this to know what it's doing. So inside the circuit direct interface, the antenna single impedance close to 50 ohms, and we go a bit further down, we see a block diagram, how it works. You're going down some more information, some general description, and this is what we're kind of looking for. It is a simple schematic diagram, reference diagram that you will use in your design to ensure this microcontroller actually does the job. So it's telling you that the crystal that we need, telling you the decoupling for this portion, and the filter and matching network, and it's telling us to refer to AN5165. This would be an application note on antenna filter and matching network. So let's take a look at that. Here we are at AN5165. Development of RF hardware using STM32W microcontrollers, exactly what we're looking for. We go down, it's quite a useful application. It gives you a bit of what you're exactly looking for and a bit of introduction, RF basics, reference board schematics, PCB stack of layout recommendations, and all this we're going to get into later. But to get up and running, we're going to take a look at the reference board schematics. So here is what you're going to look for. If we have a certain package that we are using, then we are just going to take that schematic apart from it. And as you can see here, if we were using a UFQ FPN48, this reference board here, I'm not quite sure, is it QFNP8? I'll chuck an image on screen to know what it looks like. And you can see here that it's given us this matching network over here. And this is what we would take, really. It's got the part number, it's got the inductor, it's got, we would take these exact part numbers and we would implement it into our own design. So literally in this configuration, and this would be matched to 50 ohms, as it said, and they're given this extra filter here that we should really choose to implement as it's recommended by the manufacturer. And as I've said before, these type of design reference board, they're taken off the nuclear boards or whatever, and if they work on there, they'll work on your design, so better not to use them. It's also to know that this is not the only way to to match. This is one of many solutions that you are able to do depending on your requirements and so on and so forth. So use this as you would. So just to let you know that this is one of many solutions, but personally I would just take it and since I know it'll work, I would just use it in my design. No shame in copying something that already works. Don't try to reinvent the wheel. And as you can see here, there's also for this package, you can see it's the same. And as you can come to this package, you can see it is slightly different. So I would take note depending on your reference for whatever package you are using. So do take note for this. As you can see here, it's changed again. So now that we know how to do it and we are aware of what we're actually looking for, let's go over some brief notes to consider whilst we're laying this out. So here we are in Altium. I want to talk about the PCB stack up. This is just a board that I've showcased in the previous video about some mistakes I've been through. And the stack up is quite a large topic in itself, and there's quite a few things you can speak about, but I'm just going to talk about how your impedance matching will affect it. So I will go to design and go to layer stack manager. Here we are in the layer stack manager, and we see this is just a standard 2-layer board, and we see the thickness and what is it, and we go to impedance here, and we're going to add an impedance profile, and this is set to 50 ohms. That is a standard. And as you can see here, this is the trace width here. So this trace width is what you want when you design your RF lines. It should be to 50 ohm impedance unless you otherwise specify, but standard is 50 ohms. So you would always want to trace with this, always want to place your RF line with this width here, this 0.53461, and it works close as you can really. And what affects this is the thickness here and what you have in your PCB stack up. And let's see, if I change this number to 7, you can see our width has slightly changed. If I change it to, and you can see that's changed again. So this won't be standard across all PCB manufacturers, so do check with your PCB manufacturer of choice to what their layer stack up is, and do implement this into your own design. Of course, I'll show you there's other tools online. You don't need to have Altium to do this kind of thing. This is just an inbuilt thing, which is quite nice, but there are other tools online. So here we are at JLC PCB, and they have a controlled impedance stack up and whatnot. And if you scroll down, you see we're going to select our thickness here is 1.6. Depending on your board, as you can see, it does change ever so slightly. But essentially what you want to do is input these exact numbers into your thickness for your board stack up. So this is to ensure that what JLC PCB produces and what you design, you're going to get the same, or roughly, if you account for deviations and whatnot. This is a critical parameter in your designs that you should be aware of. And another thing is on layout. So your layout can actually have an effect on your RF signal. And I'm not going to go through it too much, but this application will just cover quite a bit on how to achieve a good layout practice and whatever. But let's just say keep your signals on the same layer on the top. Have a decent ground pour around them. Make sure they're short and neat. Don't have signals coming under them, or have a crystal that's nearby inducing noise and all that. So it's best to have a read through this. I'll leave this in the description. And another thing would be to pass the line through components. So what I mean by this is, let's take a look at this image here. I don't really have a design on me. It's on a different computer for the things I did. And as you can see here via this line, you could see this track here just passes through the components, and just doing a simple Google search would also aid you in this endeavor for what you want to achieve. So you can see they're all tightly squeezed to keep in the line as short as possible, and they're just passing through all the components. You don't see any curves, unnecessary curves. If you have to, you have to, but you don't see them as much. So that was all I wanted to talk about as a brief overview into what is it. Hopefully I can get out a design in the future to showcase a bit more complicated ones. I have been doing a lot more like basic overviews from past projects, but hopefully showcase a design with a bit more in-depth things to it. And that'll be a lot more better, and it gives you a lot more information, and steadily increasing difficulty to what I'm doing and things like that. So hopefully you've gotten a brief overview on what impedance matching is and how you can apply it in your circuits, and how to get it as fast as possible, I suppose, into what you do. As I said before, I've had trouble finding this out before, especially when you're new. There's so much things to cover. Hope you enjoyed the video.